Yesterday morning at 7:34 a.m. local time, the ground opened up underneath western Colombia, and it did not stop shaking for what witnesses described as some of the longest, most violent seconds of their lives. A magnitude 7.4 earthquake tore through the Chaco region. And by the time I'm recording this, the confirmed death toll has climbed past 130 people, with hundreds more injured. And buildings down in Cali, Pereira, and Manizales. Cable cars were left stranded midair with passengers trapped inside for 6 hours. A church facade came down on camera. People in Bogota, a city over 200 miles from the epicenter, ran out of their office buildings because the shaking was strong enough to feel from the capital. I want to be upfront about something before we go any further. Real people died in this event, and real families are digging through rubble right now while I'm talking to you. So this isn't going to be a disaster content video where I treat a tragedy like entertainment. What I want to do instead is actually explain what happened geologically, because there's something genuinely strange about this particular earthquake that most coverage isn't explaining well. And then I want to use it as the jumping off point for a question I get asked constantly. With all our technology, all our satellites, all our supercomputers, why can scientists still not tell us when the next one of these is coming? By the end of this, you're going to understand that question in a completely different way than you did 10 minutes ago. Let's get into it. What actually happened in Colombia? Let's start with the basics, because the specifics of this earthquake matter for the bigger conversation we're about to have. The quake struck at 7:34 a.m. local time on Monday, August 10th, with the United States Geological Survey placing the epicenter about 5 kilometers from the small town of San José del Palmar in Colombia's Choco department, a remote, mountainous, heavily forested region along the Pacific side of the country. Colombia's own Geological Service put the magnitude at the same 7.4, while some international agencies logged it slightly lower, around 7.2. Small discrepancies like that are normal. Different networks use slightly different station coverage and slightly different math to back out a magnitude, and anything within a few tenths of a point of each other on an event this large is considered good agreement. Here's the detail that I want you to really sit with, because it's the single most important fact about this earthquake, and it's the thing most headlines buried. This quake happened about 107 kilometers below the surface. That is deep. Genuinely, unusually deep for an earthquake that did this much damage. To put that in context, most of the earthquakes you hear about, the ones that flatten cities, the ones you see viral footage of, happen at what we call shallow depth, typically less than 20 or 30 kilometers down. The shallower an earthquake is, generally speaking, the more violently and abruptly the ground right above it shakes, because there's less rock between the rupture and your feet to absorb and dampen that energy. A shallow magnitude 6.5 can be more locally destructive than a deep magnitude 7.5 because depth acts almost like a shock absorber. So why did a quake happening 107 kilometers underground manage to kill well over 100 people and collapse buildings in cities dozens, even hundreds of kilometers away? This is where we have to talk about plate tectonics, specifically in this part of South America. Why this earthquake was so deep and so widely felt. Colombia sits in one of the most geologically complicated corners of the planet. Multiple tectonic plates and smaller microplates are colliding, sliding past, and diving underneath each other here. But the big player in this event is the Nazca Plate, an oceanic plate that's being forced underneath the South American continent in a process called subduction. Picture 2 slabs of material colliding, where 1, the denser oceanic plate, loses that fight and gets shoved downward, plunging into the mantle at a shallow angle, like a spatula sliding under a pancake. As that slab of oceanic crust descends, it doesn't just glide smoothly, it bends, it heats up, it gets squeezed by the surrounding. Mantle rock in ways that build up enormous internal stress within the slab itself, not necessarily at the boundary where it meets the continental plate above it, but inside the sinking slab. When that internal stress finally releases, you get what's called an intraslab earthquake. A rupture that happens inside the subducting plate itself, sometimes over 100 kilometers below the surface. That's exactly what the USGS is describing here. An intermediate depth quake generated by faulting inside the Nazca Plate as it continues its slow motion dive underneath Colombia. The reason these deep intraslab quakes can be felt across such an enormous area, even though they're less locally violent than a shallow quake of the same size, comes down to geometry. A quake 107 kilometers down radiates its energy outward in something closer to a sphere. That means cities 50, 100, even 200 kilometers away from the epicenter aren't really that much farther, proportionally, from the actual point of rupture than the towns sitting directly above it. That's why USGS shake intensity estimates for this event show something like 10 to 11 million people experiencing strong to very strong shaking, and additional millions more feeling moderate shaking as far away as Ecuador, Panama, and even parts of Venezuela. It's also part of why the Colombian Geological Service is calling this the strongest earthquake to hit the country in decades. Not necessarily because the magnitude itself was record-breaking for this region, but because of how far and how forcefully that energy propagated. One more important detail: because this quake occurred so deep inland, no tsunami warning was ever issued for it. Tsunamis are generated by shallow undersea earthquakes that physically displace a massive column of ocean water above the rupture. A quake 107 kilometers beneath a mountainous inland department, however powerful, simply doesn't do that. So while the ground shaking risk was extreme, the ocean threat here was essentially zero. And that's worth knowing because in the immediate aftermath of any large earthquake near a coastline, that's usually one of the first questions people have. Every single time something like this happens, Turkey and Syria in 2023, Morocco later that same year, Venezuela's magnitude 7.5 event earlier this year, and now Colombia, the same question surfaces within hours on social media. How did nobody see this coming? We put rovers on Mars. We predict hurricanes 5 days out with genuine skill. We have satellites that can measure ground deformation down to the millimeter. So why, Enki, in 2026, can a seismologist still not walk up to a podium and say, there's going to be a major earthquake in this specific location sometime in the next month? The honest answer, and I mean this as directly as I can put it, it's not that we haven't figured out prediction yet. It's that a huge and growing body of evidence suggests short-term earthquake prediction. Telling you the specific time, location, and magnitude of a coming quake with useful precision may not be possible even in principle, given how the physical process actually works. That's a very different, much more uncomfortable answer than we just need better sensors. And I want to walk you through why serious seismologists have largely arrived at that conclusion. Inside the lab, why even perfect conditions don't help. Here's one of the most revealing pieces of research on this whole topic, and it's not even about real earthquakes. It's about laboratory experiments designed to strip away all of the real world's messiness and test the pure physics of rock failure. Researchers have run experiments where they take rock samples, apply the exact same stress at the exact same rate, under the exact same laboratory conditions, over and over again thousands of times. If earthquake rupture were a fundamentally predictable process, if there were some clean, discoverable early warning signal buried in the physics, you'd expect these identical samples under identical stress to fail at basically the same point every time. That's not what happens. Even in that perfectly controlled environment, the exact moment of failure varies. The system is sensitive to tiny, essentially unmeasurable differences at the microscopic scale. A slightly different arrangement of grains, a microscopic flaw here rather than there. And those tiny differences cascade into meaningfully different outcomes. That's the signature of a chaotic system, in the technical sense of that word. Not random exactly, but so sensitively dependent on starting conditions that predicting a specific outcome requires a level of precision in your input measurements that simply isn't achievable. Now scale that up from a rock sample in a lab to an actual fault system. Hundreds of kilometers of rock, buried kilometers, underground, with variations in mineral composition, fluid content, pre-existing fractures, and stress history that we cannot directly observe at anywhere near the resolution those laboratory experiments could control for. If perfectly identical lab samples produce unpredictable failure timing, the idea that we could predict the exact day a real fault will rupture starts to look less like an engineering problem waiting on better instruments and more like an argument against short-term prediction as a workable goal at all, even with future technology. For decades, researchers chased the idea that some measurable signal, a precursor, reliably shows up in the hours, days, or weeks before a major quake. It's an intuitive idea, animals acting strange before a quake, changes in radon gas seeping up from underground, odd electromagnetic signals in the atmosphere, small shifts in groundwater levels. If any of these turned out to be real and consistent, we'd have something to build an actual short-term warning system around. The problem is that when these proposed precursors get tested rigorously against large data sets, rather than cherry-picked after the fact from a handful of famous earthquakes, they consistently fail to hold up. One review of proposed electromagnetic and geochemical precursor signals found that the vast majority failed, the large majority of validation tests, meaning the signal that seemed to show up before one earthquake either didn't show up before most other earthquakes, or showed up plenty of times when no earthquake followed at all. That second failure mode is just as damning as the first. A warning system that cries wolf constantly is arguably worse than no warning system because it erodes public trust and leads to systemic complacency exactly when a real signal eventually does appear. The USGS's own public position on this is about as blunt as a government science agency ever gets. Neither the USGS nor any other scientific institution has ever successfully predicted a major earthquake, and they do not currently expect that to change in the foreseeable future. That's not a hedge. That's decades of accumulated null results from a global community of scientists who, frankly, would love nothing more than to be the team that cracks this. There's no shortage of motivation here. The fame, the funding, and, above all, the potential to save enormous numbers of lives would go to whoever solves this problem. The fact that nobody has, despite that incentive, is itself part of the evidence. What we can do instead, and why it's not nothing. Here's where I want to pivot, because we can't predict earthquakes is not the same statement as we know nothing useful about earthquakes, and I don't want you walking away from this thinking seismology as a dead end. It's not. It's just aimed at a different, more achievable target, probability, not prophecy. Long-term forecasting models like the ones used for California under a framework called U-Curve 3 don't try to tell you that a quake will strike on a specific date. Instead, they integrate decades of data. How fast different sections of a fault are creeping, where past ruptures have occurred, how individual fault segments connect to each other, to produce a statistical statement, something like a roughly 7% chance of a magnitude 6.7 or larger earthquake striking Southern California within a given year. That's genuinely useful information. It's exactly the kind of thing building codes, insurance markets, and emergency planning budgets get built around. It's just categorically different from telling a specific town, evacuate by Thursday. GPS networks add another layer to this. Modern satellite geodesy can measure the Earth's surface creeping along a plate boundary at a rate of just a couple of centimeters a year. Astonishingly precise. When researchers see a section of a fault that's not creeping at all, while the surrounding sections are, that tells them the fault is all locked, stuck, accumulating strain. That isn't being released gradually, which means it's storing up energy for eventual release all at once. Colombia itself sits in one of these tectonically loaded zones at the convergence of the Nazca, Caribbean, and South American plates, which is exactly why the region has such a long history of significant seismic activity. Knowing a zone is locked and loaded tells scientists it's a place worth watching closely, worth building stricter codes around, worth prioritizing for early warning infrastructure. It still doesn't tell them the quake is coming next Tuesday. Paleoseismology fills in an even longer timescale. By digging trenches directly across fault lines, geologists can physically see and date the disrupted soil layers left behind by ancient ruptures going back hundreds or even thousands of years, reconstructing rough earthquake cycles, sometimes on the order of one major rupture every 100 to 300 years for a given fault segment. That helps researchers understand which faults are due in a very broad statistical sense, the same way you might know a 90-year-old is statistically more likely to pass away this decade than a 20-year-old, without being able to name the specific day. The one thing that actually does work. Early warning. I want to draw a hard, clear line here between two things that get confused constantly in headlines and honestly in casual conversation too. Earthquake prediction and earthquake early warning. They sound similar. They are not the same thing, and the distinction matters enormously. Prediction, in the sense we've been discussing this whole video, means telling you in advance, hours, days, weeks, that a quake is coming. That's the thing that doesn't work, and based on everything we just covered, may not be achievable even in principle. Early warning is different. It doesn't predict anything before the rupture starts. Instead, it detects an earthquake in the first fraction of a second after it has already begun, and uses the fact that the data travels near the speed of light through fiber optic cables and radio signals, while the actual damaging shaking travels through rock at a much slower speed, several kilometers per second. That gap, tiny as it sounds, can translate into anywhere from a few seconds to, in some cases, over a minute of genuine warning for people farther from the epicenter than the initial sensors. Systems like this already operate in Japan, Mexico, and here in the United States along the West Coast, automatically slowing trains, opening elevator doors at the nearest floor, and pushing alerts to phones in that brief window before the shaking arrives. It's not prediction, it's detection plus a physics head start, and it is right now the single most effective technological tool we actually have for reducing casualties from a quake that's already begun, and why this matters for how you live, not just what you know. So here's where I land this, because just like with any disaster content I make, I don't want you walking away with only information. I want it to change something about how you're prepared. If you live anywhere near a known fault system, anywhere along a subduction zone like the one running through Colombia, or the Pacific Northwest, or Japan, or Turkey, or Chile, the operating assumption has to be that the warning, if it comes at all, will be measured in seconds, not days. That changes. What preparation actually looks like. It's not about watching the news for an alert to evacuate ahead of time, the way you might for a hurricane. It's about having your response already built into muscle memory before anything happens at all, knowing the drop, cover, and hold on response cold, having heavy furniture secured to walls, knowing your building's structural history if you live somewhere with older, unreinforced construction, and having a family communication plan for the very real scenario where cell networks go down right when you need them most. The people in Bogota who evacuated their office buildings yesterday did the right instinctive thing. The tragedy in Colombia right now isn't a failure of prediction. Nobody on this planet, with any tool available in 2026, was going to see this specific rupture coming with enough lead time to matter. What separates a survivable earthquake from a catastrophic one over and over again across the history of seismology comes down to building codes, structural retrofitting, and how fast people react in that first 10 seconds, not advance warning. To bring this all the way back together, a magnitude 7.4 earthquake ruptured roughly 107 kilometers beneath western Colombia. Yesterday morning, inside the Nazca Plate as it continues its slow subduction beneath the continent, and that unusual depth is exactly why the shaking radiated outward across such an enormous swath of the country, killing well over 100 people and reaching cities hundreds of kilometers from the epicenter. And when we ask why nobody warned Colombia this was coming, the answer isn't a gap in our technology waiting to be filled. It's that the physics of fault rupture appears to be genuinely, fundamentally resistant to short-term prediction, something laboratory experiments on simple rock samples demonstrate even under perfectly controlled conditions. What we do have: probabilistic long-term forecasting, GPS-based strain monitoring, and genuinely life-saving seconds to minutes early warning systems isn't a lesser consolation prize. It's the actual honest frontier of this science, and understanding that difference is what should shape how seriously you take preparedness in your own life, wherever you're watching this from. If you found this useful, I'd ask you to do one thing. Go check whether your own home or workplace actually has a real earthquake plan, even if you don't think you live somewhere at high risk, because plenty of the people affected yesterday didn't think they lived in a high shaking zone either. Stay safe out there, and I'll see you in the next one.